Ferrous metals that contain a certain amount of carbon are hardened when quenched. This section briefly explains the mechanism of the hardening in terms of metallurgy. First, let me review a little more detail about what hardness means. When a force above a certain magnitude is applied to a metal, the metal enters the plastic range and leaves permanent deformation. Hardness is assessed by the depth remained by sharp hard tip pressed on a metal. So, the hardness is defined as a quantified measure of resistance against plastic deformation. Iron atoms are bound together by metallic bonds. To understand the mechanism of quenching, we need to understand how metals, including ferrous metals, are deformed from the viewpoint of atoms. Iron atoms are bonded and arranged together by metal bonds. Now, we are thinking about applying a force to deform them. You may imagine each of the metal bonds breaks and the arrangement of atoms shifts in the metal deformation. In reality, however, these metal bonds are quite strong, and it is not easy to break all of these bonds to displace the arrangement of the atoms. Now, we are arguing about what is going on with the atoms and bonds when a metal deforms in reality. In reality, a metal does not have perfectly aligned structure of atoms as shown earlier. Metals have defects as shown in the illustration. This defect is called dislocation. A dislocation is represented by a symbol shown in the illustration. When a force is applied to a metal, such dislocations move to deform the metal. You may notice that far less force is needed to move the arrangement of atoms than breaking all the metal bonds at once. Based on the argument before, I am now explaining why ferrous metals become harder when quenched. Plastic deformation of a metal is caused by the movement of dislocation. As we explained earlier, hardness is defined as the resistance against plastic deformation. So, hardening is equivalent to making the dislocations difficult to move. The quenching process hardens the material. So, quenching makes the transportation of dislocations more difficult by using heat treatment processes. We should focus on what exactly is happening to understand the mechanism of quenching. Quenching is carried out by heating a ferrous metal to a state where its crystalline structure contains austenite, and then rapidly cooling it. We have already discussed that, unlike ferrite, austenite accommodates more carbon atoms as solid solution. Austenite accommodates carbon 2.1% as the solid solution. On the other hand, at room temperature, ferrite only accommodates 0.008% of carbon as its solid solution. So, carbon atoms exist as cementite bonding iron atoms. Now, we are thinking about a case where carbon-rich austenite is cooled slowly. The carbon atoms that were not included in ferrite is bonded with iron atoms to be cementite. So, at room temperature, The structure is composed of ferrite and cementite. On the other hand, in the case of quenching, we are cooling rapidly down carbon-rich austenite. Let's see what happens in this case. When austenite is rapidly cooled down, it becomes martensite with carbon atoms trapped in a body-centered cubic lattice. This state means there are a large number of dislocations, distortions of the arrangement of atoms. When a large number of dislocations exist in crystalline structure, they collide with each other and make it difficult to move. In addition, when a crystal is rapidly cooled down, the grain sizes are smaller in the crystalline structure because the grains do not have enough time to grow. So, more energy is required for the dislocations move across the grain boundaries. This is another reason why rapid cooling makes the dislocations more difficult to move. Quenching and tempering are performed in pairs. Quenching is the process to harden metals, while tempering is the process to attribute ductility on the hardened metal. What is going on in this tempering process? The tempering process involves heating the atoms to make them easier to move. Then, the carbon atoms trapped in the ferrite are then released to become stable cementite. The ratio of cementite to martensite is adjusted by the time of heating to control the hardness and ductility.